Yeah.
Okay.
Now you'll have an archive of it, which is really good. Yeah, we'll be a little bit different because some people will not.
Hey, can you join my meeting outside or something, just to make sure that the mic is okay?
Use me a link.
Oh, yeah. I'm giving my thesis defense again here.
The one thing I would do on your violence one, just treat it seriously, as in like give people a pause to say this would be a good time. If you're uncomfortable in the room, and don't just click. I don't think it'll be a problem.
Okay.
Just the link. No, you just say, just give people, don't say leave the room, just say there will be violence, and so. I just wanted to let everybody know, but just give it a pause. So if somebody actually makes a motion to leave the room, we get the opportunity.
Okay.
All right. Okay, so let me just check one thing over there.
Slack message. Wait, when we hear it's kind of good for me.
That's fine. I mean, if we hear the weird thing, that's a good thing.
Yeah. Hey, Kayvon, can you hear me? And am I look good on the video? Let me see how I look.
Yeah, okay. All right.
Wait, can I just see myself? Can I just?
Yeah, you'll find. All right, hey everybody. Okay, so for those of you that are used to sitting over there, you might want to reorient for this part today because David's physically plugged in. I was on airplane, which allows me to stand it, but I'll give everybody a chance to move over. There's still plenty of seating here. Okay, so while everybody moves, okay, so we've been talking in this class about like this year was kind of the generation year that we threw a bunch of generative content into the class. And as you all know, we finished the generative content with, it's not just images, it's not just videos, it's not just 3D meshes, but it gets really interesting when what we are generating are behaviors or problem solving skills. Like that was the theme I'd like you to take away. Do we have, how many more lectures? We have this week 8, right? So we have 2 weeks or 2 classes this week, 2 classes next week. And then the final Tuesday on the last day. Now that final Tuesday is project presentation day. So everything is due on that day, on that Tuesday, with, remember, no penalty for handing in your final write-up as late as 11:59 p.m. the following Thursday. Okay, so that's the rest of the class. So today, what we got the opportunity to do is David is here to talk to us. Now, David's a PhD student in the graphics lab, and David defended his thesis on Friday, so he's now a doctor. This talk is pretty relevant to the course, and so we have the opportunity to snag him to give you all the talk. And I think it's a pretty different approach from what we talked about in class. Like in class, we talked a lot, in class we talked about 2 major approaches, right? One is we can learn behaviors by trial and error, and we need to take a billion trials and errors. And then everything else we talked about in class was if we just had all the data in the world of examples, let's just learn how to follow the examples, basically. And that's what we did for images, that's what we did for video. And David's going to give the other perspective on behaviors today, which is, hey, if you happen to have a ton of training data for how people do things, maybe you can build an intelligent agent pretty quickly, right? So this will be David's thesis talk, but this is a class, so I want to encourage everybody to ask questions at any time during this talk. The only other thing is that just for archival purposes, I'm having David record his screen share, which will capture audio in this room. So if you're okay with that, I would love to just have David be able to take this full thing unmodified. If by any chance you want, like you ask a question and you want your voice scrubbed from the audio track, can you please let us know so that we just make sure that if David ever shares this with somebody, your audio is not caught. Okay. All right. Why don't you get started? Okay.
Okay.
Sit over here and listen.
Cool. So Thanks for coming, everyone. As you mentioned, I'm David Durst. I'm one of his students. Always like to repeat my name. And I'm going to be talking about efficiently imitating human movement in Counter-Strike. And yeah, good. And so before we get started, just a brief content warning. There will be video game violence in this presentation. Look, Counter-Strike is an excellent test bed for creating bots, but it's also a violent video game. And I've done the best to minimize that violence where possible. Okay, so there's a lot of people in computer science interested in modeling human behavior, from financial transactions to self-driving cars in San Francisco to, your favorite AI agent driven by an LLM. But, I'm in a graphics lab, and I want to work on modeling human behavior in video games, where we can use these models to detect antisocial behaviors or to teach complex team-based behaviors to newer players. And today, I'm going to focus on one type of video game, first-person shooters, or FPS. And in particular, one type of game, Counter-Strike, which has a lot of interesting team behaviors. And for the last 3 years, I've been working on AI agents, or bots, that can play a subset of this game. Since I assume most people here aren't familiar with FPS games like Counter-Strike, give me a few minutes to give a quick intro to the genre. Humans have some pretty common sense behaviors that are really easy to understand, but devilishly complicated to implement. And my cool result is that I've created bots that imitate these behaviors. So Counter-Strike is a team-based game where people spend decades playing on the same map, and I focus on one map that's the canonical example. And in this map, there are 4 guys on offense, who I'm going to refer to as the blue team, and 3 guys on defense, who I'm going to refer to as the yellow team. And the blue team's objective is to capture the bomb, highlighted in red here, which you can think of as just standard capture the flag. And the yellow team tries to stop it. Now, of course, this being a first-person shooter, these teams try to accomplish their objectives by shooting each other and using some common sense behaviors. So the first behavior is positioning. Here, humans position themselves near walls, known as cover, in order to protect themselves from enemies. So we have 2 guys, a blue player standing close to a wall, in order to hide himself from a yellow defender standing above him. And side note, the lines you see showing where the people are looking aren't visible when you're playing the game. They're just visible for demonstration purposes only. And of course, when humans are ready to fight, they stand in a place where enemies can see them. Like how this blue guy is standing now far away and can now see the yellow enemy. And of course, people don't really stand in the open because then they can get shot without being able to see everybody. And sorry, one sec. And unlike prior bots, I've created bots that imitate this behavior. So I don't really want to get into the weeds of this result because it's only a sneak preview of what's going to come later. But on the right here is a heat map showing the distribution of where my bots travel over 1,430 games. And the red region shows where they travel a lot, and the blue region shows where they travel relatively little. And we can see that my bot uses this wall to hide and uses this wall to engage the enemies, and never stands in the middle in the blue region, which makes it vulnerable without providing an advantage. Now, the second behavior is pretty obvious. You want to make sure that you actually react to the enemies. So if the yellow defender stands in this region in the doorway, and there's a blue player way behind him, behind a wall, about to defuse the bomb, and he hears them in that direction, then of course, the yellow defender better move in that direction. And again, if we play a video of my bot, it will react accordingly. And alternatively, if the yellow defender starts in the same place, and the blue attacker, he hears him coming from the opposite direction, then the yellow defender better move in that direction to stop the bot. So again, when we play a video of my bot, it does the appropriate thing. And finally, the most complex movement behavior that we're going to discuss in this presentation is flanking, or attacking from multiple directions simultaneously. So in this example, one player is going to attack from the red door, one player is going to attack from the blue door, and one player is going to attack from the green window. And everybody needs to enter simultaneously, so the defense has to deal with them all at the same time. So we're going to watch a video of my bot flank. And again, all the different players here are controlled by my bot. And the blue and the green bots are going to get in position, get ready. The red guy is going to take a while. It takes some time for everyone to get into position. And then finally, when everyone's ready, everyone's going to enter all at the same time, and we're good to go. And finally, after a little bit of combat, things will break down. Okay. So in addition to imitating all of this behavior, there's a key constraint. The behavior generator must run in real time in a game. And the AI budget for most modern games is a few milliseconds on a single CPU core. No GPUs allowed. So what I've been working on for the last 3 years is to show that it's possible to generate this behavior within the AI performance constraints of a game. And I did it by taking a data-driven approach with machine learning to learn the movement. And then I combined it with traditional rules-based approaches in order to build a complete bot that plays Counter-Strike. And altogether, I'm going to show you that I can generate the interesting team-based behaviors that humans have, and I can do it within a tight budget. Now, I needed to create a significant system in order to make this work. And the system consists of 4 key components. First, I'll explain how I curated a large data set, and I ended up creating the first data set from pro gameplay logs for learning movement in a team-based FPS. Then I'll present the design and training of my model. It's inspired, it controls the movement of all the bots simultaneously using a small transformer, and it's inspired by the trajectory prediction literature from self-driving cars. Third, I'll demonstrate the model inside of a full bot that plays Counter-Strike, which humans have played with and against. And finally, since I'm interested in imitating since I'm interested in imitating humans, I needed to think a lot what it means to be human-like. You know, a core tenet of the thesis is that if bots are human-like, they'll be more engaging and more useful. But defining humanness, particularly movement, is not well agreed upon. And so I'll talk about how I measured the humanness of movement for various metrics and ways of playing with and observing the bots. Now, of course, I'm not the first person to build bots for complex games. You know, we have DeepMind, OpenAI, Fair, and a host of game companies. And they've all trained bots for a range of really complicated games. But the challenge is that none of these approaches simultaneously generate the human-like behavior that I'm trying to imitate in a complex FPS, while satisfying the game's performance constraints. So look, reinforcement learning agents have generated superhuman behavior in a range of really complicated games, from strategy games like Go, to StarCraft, to Dota. And they've also worked in first-person shooters like Quake 3, and even racing games like Gran Turismo. But when people actually shipped these in a commercial game like MotoGP, they weren't particularly engaging, and they weren't very human-like. And there's a result from the academic literature on diplomacy that pure reinforcement learning approaches don't lead to gameplay that humans want to play with. I'm happy to get into the weeds further if people are interested, but the high-level bit is that these reinforcement learning bots weren't engaging because they didn't generate the strategies that humans expected for the target skill level. And so promisingly, though, imitation learning approaches trained from human data are able to generate human-like behavior. And so I went with an imitation learning approach. However, imitation learning approaches don't apply to modern games, or modern FPS games, pardon. So some, like Fair's diplomacy agent, don't satisfy the performance constraints, generating movements about 100 times slower than is necessary for an FPS and requiring orders of magnitude more compute with a bunch of GPUs. And then commercial game developers have deployed imitation learning agents for quite a long time now, but they focus on game genres that at least seem simpler than a first-person shooter. Things like a 2D fighting game or a racing game where you're following a predefined track. But I haven't seen anyone successfully deploy an imitation learning agent in a first-person shooter. Prior imitation learning work on bots took a pixels to actions approach where they tried to directly learn what to do from the rendered screen image. And as a result, they were way too expensive for a commercial game, requiring a GPU for every agent to both render the game and process the pixels. And this is about 800 times greater than the compute budget for an FPS game. Also, they focused on a seemingly simpler game mode, which didn't have a significant complex teamwork. Now, the industry standard approach to defining FPS bots is handcrafting a hierarchy of rules. And these rules break the problem down. In Counter-Strike, there are typically three main components to the problem: moving, aiming, and firing. Now, I was able to generate fairly human-like behavior for aiming and firing using rule-based approaches from industry sources. But I've never been successful on movement, and I haven't really found examples of success in industry either using rule-based approaches. Even the most painstakingly handcrafted controllers fail to handle all the different situations that can occur in the game. You just can't cram enough heuristics in to address every possible situation. So my approach is a transformer-based movement model learned from traces of human gameplay and then integrated into a hierarchy of rules that handle the rest of the game. And I was inspired by work in the self-driving car community, which found that imitation learned transformers trained from massive data sets are really good at learning the relationships between pedestrians and other cars surrounding a self-driving car. And just like the self-driving car community, if I wanted to imitate human movement, then I'd need a large data set. Oh,
Before you go to the next section,
yeah.
I was actually curious for the audience, which is how many people have played games against like these fairly sophisticated AI characters? Does anybody have any experience playing with any of these? I'm actually curious. What were your reactions? Like, is your reaction similar to sort of what the Reddit says, where people don't find these things fun? What do they do? I'm curious because there might be more people here than.
Yeah.
In Counter-Strike, they have them, and in a lot of other games they do as well, and they always have these edge cases that don't really work. And their movement also is very funny. I think that is the hardest part because you can code like the ability to use and everything, but the movement is very hard because the game is so much.
Anybody play any of the other ones? Yeah.
I used to play a lot of Call of Duty, and every time I tried to play against the computer, it was just extremely odd because they would be walking towards a wall and then like point 360 to immediately like catch me on the other side, and it was like, what is going on? Completely, yeah, like it's just not fun because you can't predict what they're gonna do, and it doesn't make any sense. Like it's not anywhere close to what playing with other humans would be like.
So, yeah.
I've had a bit of a different experience with games that involve like really complex strategy. I've noticed that there's nothing I can do to win. Just because it's played billions of games.
What example game do you play?
It was like, well, this is one that I did myself, but it was like an arena with cars that you try to hit the other cars like heads. There's like a head sticking up. So it would learn the physics so well that you couldn't do anything.
So the RL bots are just too good. Okay. So this argument makes sense.
Yeah.
Okay. Cool. Good. Interesting.
Glad. Okay. No, it's always good to have people agree or disagree. Yeah. So we're ready now to talk about the data set, because obviously if we're going to imitate humans, we need a data set of human behavior to imitate. fortunately, there's a website called HLTV with a lot of pro matches recorded at 128 hertz. And I downloaded about 1,300 of those matches and parsed the logs to extract the game state, like player positions, as well as key events, like where players were eliminated. And from these logs, I extracted a large, clean, and rich data set with 123 hours of gameplay at 16 hertz, with over 2,000 unique players, over 500,000 shots, and over 29,000 eliminations. And when we look at the coverage of the map, where each bin here is roughly the width of one player, and each color indicates the number of data points in that bin, and we have up to 100,000 data points in a single bin, we have quite a bit of data from these logs to cover the map.
I'll jump in on this something. So just because this is something you'll see a lot throughout the rest of the talk, there's like a heat map of just where people stand. So if there's a person second, now this is the number of person seconds.
It was it was a person frame, person frames at 16 hertz where people are standing.
And one thing I've always been interested in, like they take pretty natural, like curved paths everywhere except like there's those two straight lines. Like, do you know what that is?
Here,
And then there's like a smaller, like a lower.
oh yeah. So
Yeah.
okay, so for all the Counter-Strike experts, I see one person who probably played. This is a mode called retakes. And so what happens is all the action in retakes is in the two sort of objective regions, the top right and the top left. And this is sort of the line of visibility onto that objective region. And so one thing you notice when you look at the data is you would think you need to actually render the frame to learn what's visible where. But when you actually look at where players stand and where they interact, you can actually start to infer things like what the renderer would show based on where people stand. So if like, so like, for example, like this guy standing here is trying to, and I can't reach because my shirt's tucked in, but
Get the chair anyway.
is trying to look onto a guy in that hot region in the top right. And so this is sort of the place where you can stand, where the very tippy top of your head stands above a curve and lets you see it. And so when we look at these maps, like when I started this project, I thought I would need to render everything to accurately compute visibility. And one thing you learn by looking at this is raw movement and raw positions and key events is a very rich source of data for learning things about how people interact without looking at the renderer output.
Yeah, I was just wondering, if you could, like, is there an example of like a human-like movement that you would want that, like, that A isn't just the strategically optimal bot behavior, and B isn't the strategically optimal bot behavior under some constraint, like, don't change direction more than 60 times a second or something that you would never do. Because if that's not the case, then couldn't you just train a bot under some constraints to find an optimal policy for movement?
I would say, so one of the challenges that we run into is that we're not just trying to find the optimal strategy. Like I would say humans will do a diverse range of strategies. And one thing you might find when you do it, bots, it finds the one perfect one. So like the spread of like which of the two walls to pick there. Like you might engage, you might cover. There are multiple options and you don't want to just pick the same one. Or the ability, hey, if you don't want the bot to always do self-play, face something that converges to an optimal strategy. I guess I know there are counter examples where you do a range of policies from self-play and RL to counteract some of this. Let me think.
I think maybe,
yeah.
Maybe you can take the discussion in a slightly different direction. Is you are hypothesizing that you can put a set of constraints on the learning procedure that model the dexterity of a human.
Right.
As well as presumably model what the human does and does not know.
Sure.
Right,
Yeah,
like
this isn't like the StarCraft thing.
Yeah, so now you're thinking about modeling visibility. Now you're thinking about modeling, I'll let you.
Yeah.
The audio channels, because people are talking in a team-based game. And then you're also thinking about modeling a priori plans that we have decided we're going to do in certain situations and stuff like that. So my hypothesis, and this is just a hypothesis, is that it would maybe be difficult to recover human-like strategies. And you would get some human-like strategies, but you might also see gameplay that's very different because it would be very difficult to put the bots in a state space that was approximately equivalent to the state space that you have. especially in a team-based game where like half the information is over Discord. That would be my guess.
So this is a question from active CS player. So I know like you did not really mention you model the utility use
Okay.
in the game, but like for instance, utility use really matters in how the position of the bot.
Yeah.
For instance, on the left panel, you can see a very high frequency part where people really stay there because they got blocked by the smoke of the fire,
Yeah.
not because for some abstract reason. How do you like?
For this project, we're not going to model smokes, and we leave those out of the scope, out of scope.
Yeah. So how do you eliminate those effects on interpreting your position data?
Yeah. For right now, we just look at it in the aggregate, and we find that the results are pretty reasonable. I would understand that obviously a next step to the project would model these more complex behaviors. So yeah, well, I would say future work. Yeah.
Did you keep track of anything like average max length? Because I've noticed something in like, I mean, in like CSGO, the current bots will just stand still for like long periods at a time. I mean, that is like a regular human behavior also, so
Yeah.
could be like different duration.
I would say that one of the core challenges with these bots is I would say, yeah, we do have stuff metrics that aren't in this presentation, but
Let's do this.
Oh.
Let's get through the methods
okay.
and then hold your question. It's a fantastic question. Let's talk about that when we, one of the big things in this class is we've looked at a lot of other papers and been fairly deep dive, critical and supportive of how they evaluated things.
Okay.
So let's get to how David evaluated things and then come ready to throw stones.
Okay. Okay. So great. So also, oh, wait, let me pull back. Sorry, I gotta get back in the flow of things. One sec. Okay, there we go. Wrong direction, but we're going. Okay. So in parallel with my project, others have developed similar data sets. But when I started on this project, I didn't think they're appropriate for learning movement because they focused on things like high-level analytics. Now that we understand the data set, let's look at the learn movement model that I trained from the data. The goal of the model is to predict each player's next movement action, given their current position, and important game state like the location of the bomb and the time until it explodes. Now, player movement depends both on relationships with enemies, so they know where danger is going to come from, and teammates, so they can coordinate strategies like flanking. Now, inspired by self-driving cars trajectory prediction, I also use a transformer-based architecture to learn actions from states. And the key idea is to treat movement prediction as sentence-to-sentence prediction, where each word is a player's position, and then the input sentence is 10 tokens describing all players' current positions. The output is 10 tokens describing their next movement actions. And the transformer's attention mechanism learns the relationships between different players. However, pedestrian movement in self-driving cars is fundamentally different from human movement in a first-person shooter. Since I built a model for FPS, I needed to tailor that model to my application. And so I'm going to tell you guys about some of the design decisions I made to perform that tailoring. Now, one of the first questions I had to think about was, what's the granularity of my predictions? Should I predict movement only for the next 10 seconds? Or, like in self-driving cars, or only the next frame? Now, for my work, I'm going to predict over the next 3 time steps, about 375 milliseconds. And look, the reason is that Counter-Strike is a really fast-paced game where the state changes really drastically. So, in the next half second, this yellow player might eliminate this blue attacker. Then half a second after that, this blue attacker might eliminate this yellow defender. And since the state of the world changes so quickly and then invalidates the predictions made by any model, it's not worth it. It's like to do a self-driving car style approach where you predict long into the future, over a 5 or 10 second time horizon. In Counter-Strike, it makes much more sense to have a simple model run over and over again to predict the immediate future, rather than a big model that predicts far into the future. And one benefit of this approach is that I only need to use a transformer encoder, which predicts all tokens in parallel and thus runs faster. If I had a long output sequence with a lot of causal dependencies between tokens, then I'd need the sequential transformer decoder. The second key decision was specializing to a single map. Look, self-driving car models need to generalize to a lot of different road geometries. But with Counter-Strike players do play multiple maps, but they spend decades playing on each map individually and specializing to each one. So it's perfectly reasonable to specialize my model to each map. Now, the typical way to generalize across maps is to add tokens describing the geometry. But these tokens slow down performance since attention scales quadratically with the number of tokens. Since I'm specializing to a single map, I don't need them. And also, please note, this specialization doesn't mean the model architecture is limited to one map. If you get more data to cover different maps, the model trains in about an hour and a half on one GPU, so you can easily retrain it when a new map to a new map with more data. The third key decision was designing the action space. There are two non-obvious features of human gameplay that impacted this design, the action space design. First, in many situations, humans might have multiple reasonable actions. For example, the player might run directly towards the bomb site to take the shortest path. Or he might take another path that the defense isn't expecting, but is longer and slower. But he's highly unlikely to run directly into a wall or to take a path that will never lead him to the bomb site. And second, these modes are pretty sharp. So for example, consider this player standing on a ledge. And if we zoom in, we're going to notice that, in fact, he's standing so close to the ledge, he's actually levitating and not standing on anything at all. And given this precarious position, he's not likely to run forwards because then he's going to fall off the ledge. And he's not likely to run to the side because he's going to run into the wall. And he's not going to run at a 45-degree angle because, again, he'll run to the wall. But he may walk very slowly at a very specific angle in order to keep his balance to the ledge, or he might jump up on the side. So the action space needs to model both this sharpness and multimodality. And some of the most obvious approaches, like an L2 loss, won't capture the multimodality, and a discrete action space with too few options isn't gonna capture the sharpness of the modes. So while there might be multiple options that are reasonable here, I went with a cross entropy loss and a discrete probability distribution with 16 directions, 3 speeds, 2 heights, and one option to stand still, yielding 97 options. Although, of course, I'm not claiming this isn't the only possible option, but it's the action space design that worked for me. The fourth key decision was allowing attention between all living players. In a multiplayer FPS, the interaction and coordination between players is really complicated. I chose to unmask attention between all players so I can learn dynamic connections between them. Teammates always know each other's positions, but the connection between enemies is dynamic depending on things like visibility, communication between enemies, and other methods of gathering information like audio signals. So this will be reflected in the data as the model learns how attention varies depending on the game situation. And for example, this yellow defender in the top right may know about both of the attackers, including the one he can't see, because his teammate in the top left might be warning him and yelling out to him, "Hey, watch out for this guy." And so my model is going to imitate this human movement without replicating all the complex human interactions by learning the behavior from the data. Go ahead. Yeah, what's up?
So it's not visible, right? But he knows about it generally.
So some situations he might, and some he might not know. For example, if the guy was able to position himself there without making any sound, and no teammate was there, then he might not know about him.
Right, so how do you handle, like, what does his position look like? Is he just excluded from, like, the attention block?
No, so this is the key, that we're going to let the model learn his important. So we're going to let the model learn how important that not visible blue guy is to the yellow guy's movement during training.
So all of it's available to the model.
Yes, so yeah, all of it's available to the model, and we'll let the model decide during training how important that is. Was there a question? Okay, cool. And if I missed your question, please shout. I don't want to ignore anyone. Huh? Oh,
In this room, some people are behind polls.
oh, okay, yeah,
You gotta look sometimes.
it's cool. Okay. Oh,
Sorry, I have another one. Couldn't it learn to cheat then?
that's a very good question. If the reward function was to optimize winning, like a reinforcement learning approach, we would be very concerned about it learning to cheat. But since the reward function is to imitate what the human would have done, then we're going to let the model do whatever it has to figure out how to do what the human would have done. And so the goal here is yeah, just we're not trying to replicate how the human thinks. We're just trying to replicate the function of, given this state, do what the human would have done. Cool. The final key decision was only providing the current input state to the model. So while there might be a lot of different ways to use history, supervised learning has a well-known problem known as the inertia problem, which is that it's hard to learn diverse behavior when one common behavior dominates. And in an FPS game like Counter-Strike, where there's a dominant mode, but also a lot of interesting behavior in the smaller modes, this is a really important data imbalance problem that we want to highlight the smaller modes. So, for example, to understand this problem, let's zoom in on one player. In most cases, this player will move to the left because that's what they were previously doing. And one thing we can do is we can look in the data and we can see this trend. So here's a chart which shows how frequently players keep repeating the same action. If they were moving, they're going to keep moving. And if they were standing still, then they're going to keep standing still. And this is compared to changing between standing still and moving, where we can see that this only occurs in about 15% of 125 millisecond intervals. But when players are in combat, they're much more unpredictable, moving left, right, in order to dodge bullets and be a more challenging enemy. And again, I see this in the data, where if we compare the distribution of overall movement on the left to the distribution during the 2 seconds before a player kills an enemy, we can see that changing actions is about 3 times more common during combat. And combat's really important. So I want my model to express this behavior. But with history, this doesn't happen. The problem is data imbalance. Since combat's only about 0.1% to 2% of the data, depending on how you classify it, the model doesn't focus on it during training and just repeats its prior actions. And if I could identify all the different combat events, then I could use techniques like reweighting to increase their importance during training. But it's really challenging to identify all the different combat versus non-combat events. And when I tried to identify all the combat events, I could do well in the subset that I could measure, but there were a lot of things I wasn't able to identify. And so it didn't really make an impact when I played with the bot and qualitatively evaluated it. Since I couldn't get the reweighting approach to work, I just took a really simple approach of only providing the current state. Since the model doesn't have its prior states, it can't figure out its prior actions, and it can't repeat them. And as an added benefit, this improved performance since transformer attention scales quadratically with the number of input tokens. Now, there are 2 really nice consequences of these decisions. First, the model trains really fast. It trains in 1.5 hours on an RTX 4090. And second, inference is quite efficient. Its inference is 0.5 millisecond per frame amortized on 1 core of a standard CPU from 2021. So while I presented a high-level view of the model, internally the model is made up of a lot of different components. And if you guys want to talk about those details, I'm happy to do that as well. Now, I've covered the movement model. So now we're ready to talk about the complete bot that I built. to integrate that learn move model and play the full game of Counter-Strike. Now, ML Move combines the learn movement model with a rule-based state machine, where the movement model outputs a learn command every 125 milliseconds, covering direction, speed, and whether to jump. And then these commands are passed to a low-level movement controller that carries them out every frame or every 8 milliseconds by issuing keyboard commands. And additionally, rule-based aiming and firing controllers run every single frame, handling the details of that aspect of the game. These use standard industry techniques like probabilistic occupancy maps that I'm happy to discuss again if you want to talk about that further.
The fire controller is just your cursor, your crosshairs
Oh.
are near an enemy, just shoot.
The firing controller is just a lookup table. There's a little bit of detail where like you want to vary the rate at which you fire depending on which the distance the enemy's at, and you could maybe learn that lookup table. But for basic purposes, a rule-based firing lookup table is good enough. Now, the game server is going to process these commands every 8 milliseconds and update the game state. And at a overall, the high-level learn movement model takes 8 milliseconds to run when it does run, and it runs every 16 frames, which generates which results in an average or amortized cost of half a millisecond per frame. And now we can look at how I evaluate the humanness of ML Move. The fundamental question is, how well do you imitate human behavior? And I answered this in 2 ways. First, user studies. So I had the bots play against themselves for 1,430 rounds. And I had users watch some of these videos, and I had them play with them as well. And by watching and playing, they can answer questions based on how human-like the movement is. Second, I then ran analytics on the complete 1,430 round data set to get a quantitative analysis. I analyzed 4 different types of player models. First is ML Move, which is the combination of the learn movement model and the rule-based modules that I already described. The second is GameBot, which I included as an industry baseline. This is the handcrafted bot that ships with Counter-Strike.
Danica was talking about.
Oh yeah, this is the one that if you played with Counter-Strike bots, this is the one you're familiar with. Third, I agreed with you. I didn't think it was really a great baseline. So I spent 3 to 4 months writing a handcrafted rule bot that serves as a really good baseline for what bots can do in this particular situation. So it just plays Dust 2 and particularly the retake subset, and I crammed as many rules in there as I could. And this is the same as ML Move, except I replaced the high-level learn movement module with a team-based handcrafted movement module. And people on Reddit actually played with this bot and felt it was a pretty good bot relative to rule move, or compared to GameBot part. And then finally is the actual behavior of the human behavior from the data set. So for the user study, I collected 15 subjects, 9 of whom were in the top 2 ranks. These being, of course, Supreme Master First Class and the Global Elite, for those familiar with Counter-Strike's interesting naming schemes. And the important thing being that these subjects really understood what human-like movement looks like. And the subjects ranked the player model based on the following statement. Player movement matches your expectation of how humans would move in that situation. And we're going to look at one video which demonstrates the types of examples they were looking at, because they saw 8 different situations, and for each situation they saw one video for each of the 4 different types of player models, resulting in 32 total videos. So in each video they had a top-down camera perspective where they could see everything simultaneously, and they had the overlays on where they could see people through walls, which enabled them to quite effectively evaluate teamwork. And this is a standard type of camera angle used for demo review and match broadcasting. And by evaluating them based on how well players match their expectations, we can see that ML Move is more human-like than GameBot or Rule Move, but not as human-like as the actual humans. The subjects reported seeing coarse-grained teamwork based on team strategies like trading, where one player serves as a distraction while his teammate eliminates an enemy. But they also reported limitations on the fine-grained teamwork, like players being too aggressive or too passive when trading. And for example, one player subject complemented two people working together, a two-man group, but not getting the exact details right. And another subject came to the same conclusions. Now, I don't want you to get into the details of these quotes right now. There's a lot of game jargon in them. When I get into the analytics, I'll explain how I quantify what these people were looking for. I also had fairly qualified people play with the bots. Me, of course, but also other people who are also skilled and are not me. So 5 experts spent half an hour to an hour playing with them. And it seems like you can have fun playing with them. But the challenge is that there needs to be more work done on study design. It's really hard for people to evaluate the bots, particularly their bots they're not familiar with, when they're so engaged in the game that they are more focused on surviving and winning than they are evaluating the bots that they're playing with. There were some high-level conclusions from everyone, like, hey, everyone's agreed that that ML Move was more human-like than GameBot. And one or two of the reviewers felt that the ML Move movement was more diverse than Roll Move, meaning that it was harder to take advantage of. But they did feel like ML Move lacked some high-frequency details. And so in order to complement this, I personally just sat down and played with the bot for a while and did sort of like a less structured free-form study where I played with it. And I found some really cool examples of teamwork, including one where the bots used teamwork to beat me, a pretty skilled player. And so in the upcoming video, you're going to watch from my perspective. And I'm going to be playing defense, and everyone else in the video is going to be a bot, particularly an ML Move bot. And what you're going to see is that one blue attacker is going to start to fight me, and then his teammate is going to show up to help. And what you'll notice is that they're standing slightly offset from one another, so they can both engage me at the same time, and I can't eliminate them with the same bullet. So we're going to watch the video, and you're going to see me, and first one guy's going to appear, and I'm going to miss him, and then his teammate's going to show up, and I'm going to be eliminated. And so this coordinated movement, where teammates move close enough to help each other, but far enough away not to block each other, is a foundation of teamwork in Counter-Strike.
It seems like some of this coordination requires like coherent actions over longer timescales.
Yeah.
You're only giving the current state of the game to the model. How is it able to maintain?
That was pretty surprising to us as well, that it seems like there's some pretty strong, that like where you're standing is particularly for this game mode where you have a well-defined objective like a bomb to move to, is a pretty strong indicator of where you're going to behave next. There are some situations where they do stand still a little bit too long, and so I would say some of the finer grained details of exactly where to enter aren't always perfect. And I would say, future work might explore, hey, how can you incorporate some longer term history to handle some of those fine grained details? Now, that was a cherry-picked example, but I can't watch all 1,430 rounds of gameplay, and I can't play with them, and I can't have all my subjects play with all of them. So what I did was I let the computer look at all 1,430 rounds with some analytics. So here we see the distribution. Oh yeah. So the first question I answered was, do ML Move and humans use similar positions? And here we see the distribution of humans on the offensive team from the 1,430 rounds of gameplay. And each pixel shows the number of game ticks when offensive players occupied that region of the map. The scale on the right shows the mapping from colors to use. And I'm going to highlight two regions in particular, Region A and Region B, at the bottom of the map. When I look at the same data for ML Move, I see a lot of notable similarities, although there also are some differences that I'm happy to get into if you want to discuss those weeds. But in particular, highlight A and B look pretty similar. Now, both the human and the ML Move have a lot of density at the top and the bottom of the region. And these are the walls that we saw in the intro, where the top wall provides cover from the enemy standing above, and the bottom wall enables visibility onto the enemy standing above. And multiple subjects complemented ML Move on good use of positioning and cover. And in Earth mover's distance quantitatively supports this analysis. So this metric shows the difference between the distribution of positions for the human player for each bot and the humans. So lower is better. And I ran the analysis over the 1430 rounds 5 times. So I played the 1430 rounds 5 different times and then computed Earth mover's distance over all the different combinations. So what you see are the median and IQRs of the Earth mover's distance across those 5 different trials. And that assures us that there should not be much of a statistical aberration here. And we can see that ML move is much closer to the human baseline. The second question I answered is, how often do teammates coordinate? I answered the question by looking for coordinated movement like flanking. This is the stuff, again, you saw in the intro, where multiple players are going to attack from the same time and all enter at the same time. So you're going to have one red player attack from the top door, one player attack from the blue door, and one player attack from the green window. And everyone's going to have to enter all at the same time, so the defense has to deal with them simultaneously. Again, we saw this in the intro, but reminding everybody, we're going to watch as the blue guys and the green guys are going to get set up while the red guy takes time. And this is going to take some time. It's going to make the presentation run a little bit longer, but eventually the red guy is going to get into position and everyone's going to enter all at the same time and we're ready to go. Eventually, of course, this is all going to break down due to combat. But flanking is really tricky because there are lots of different ways to flank. And we don't want to just hard code like 3 guys always come from 3 different directions. So here, for example, 3 teammates might come in a different setup, like 2 from the blue door and 1 from the green door. And we're going to watch this example where the attacker is first for the green door, is going to get set up, and he's going to have to wait for his teammates, who are going to take a little while. And by the way, this is the same example of me fighting with the bots. So I'm the yellow guy in the top of the screen, and everyone else is one of my bots. When I'm eliminated, it's go time, and everyone's going to enter. Now, I want to point out an expert level detail that the subjects commented on when they were reviewing similar details in the user study that wasn't exactly perfect. One user said, but the 2-man CT push swung a little wide toward Big's box, huge exposure of backs to all of car/tunnel side. Now, this is a whole lot of jargon, but what it means is that the 2 attackers coming from the blue door generally did a good job, but at the end got too far out in the open away from cover and too near a region called Big Box, so they could be shot in the back from an attacker coming from a region known as upper tunnel. And this game jargon, like upper tunnel, is key to quantifying human teamwork. So gamers have already given names to all the different regions of the map. And so I'm going to define a flank as when attackers are in those specific regions of the map. So the flanks I just told you about were coming from upper tunnel, B doors, and hole. And so I measured the frequency of 5 popular flanking strategies that I know to exist in Counter-Strike. So the chart on the right shows the absolute error between the sorry, I need a drink of water. Pardon, better. Okay, we're back. The chart on the right shows the absolute error between the frequency of the flanking strategies between a bot and the human. And so lower is better because it means a more similar frequency. Each situation here, F1 to F5, is a different flank, and the black bars are the interquartile ranges. I ran this over 1430 rounds 5 times, so because these metrics can be a little noisy. And across the 5 different flanking strategies, I see that ML move usually replicates the frequency of humans better than rule move and gamebot. And you can also define a similar spreading strategy for the defense. And again, I see across these 6 different spreading strategies ML move, again, replicates the frequency of is more similar to the frequency of humans than the two bot baselines. So the third question I answered is, do key events occur in similar places on the map? Now, this heat map shows the regions where humans kill from. And so each bin, shows each bin's color shows the number of kills in that region. So for example, this green region shows that there's a lot of kills from these doors because players can take a shot, and if they miss, get out of cover or get to cover and then re-engage in fighting without dying. But the red region has relatively fewer eliminations because there's no cover here, and if you ever got into an engagement here, you'd likely die and have no recourse. So ML move has a similar concentration of kills, just with a different magnitude. So again, we have a lot of focus in the green region, just with a different magnitude, and less in the red region. This showing that similar movement leads to similar outcomes of key results. Or sorry, similar distributions of key outcomes. And again, Earth mover's distance quantitatively confirms this, where we can see that we're more similar to the distribution of kill locations for ML move than the two bot baselines. And finally, since I'm using a transformer, you might be wondering, how does the attention mechanism contribute to these results? So on the left, we're going to see two blue offensive players, P1 and P2. And they're standing near each other and they're attacking. And there's one yellow defender who's near them, P3, and one yellow defender who's really far out of the picture, P4. And we can see the attention matrix showing the relationships between the tokens for the different players. And each row here is going to show the source of the attention, and each column is going to show the target of the attention. And we can see that the attention actually makes sense. So P2 is paying a lot of attention to P1, the attacker who's really near him and he's engaged with, but going the wrong direction. But there's relatively little attention to P4, who the attacker who's really far out of the picture. Sorry, P2 is paying attention to P3. Sorry, not P4. Too many numbers. Getting them mixed up. Yes, P2 is paying attention to P3, but not P4. And I've also highlighted the importance of attention and ablation using, importance of attention and history using ablation. So we can see that the model does worse when you mask out attention between all tokens or when you add history. Not as bad as the two bot baselines, but this still decreases performance. So lastly, look, there's a ton of different parts to this project in addition to the model and the bot. So of course, you got to train the movement model in PyTorch, deploy it in C++ and Torch script, and build the rule-based models. But there's also a database that you had to build for extracting the data, scrape the game logs, and parse them and visualize them. But the last really cool piece, and the part that I think people should really think about, is Counter-Strike is not a game actually designed for building bots. And when you think about games that you should work on, it's really helpful to have a modding infrastructure to be able to change the game and build what you need. So I, for example, built my own interface to the bots, built my own interface to the server so that I could extract game state in real time and I could control the bots so I could deploy my inferences in game. And this took about 3 years to build, all in all. As we wrap up, when I started this project 3 years ago, I was talking a lot to some senior people at Activision. I was interning there and I was talking to them and I was sending them an email saying, I'm going to change how you think about human movement in video games and how human behavior goes. And my first project on this, my first step in this project is what you're seeing on screen now. And I had a couple hypotheses. The first hypothesis was, look, modern ML movement is just modern machine learning is just way too expensive for games. Never going to happen in a million years. Games are deployed in data centers without GPUs, and many servers are co-located on the same CPU. So we're just never, ever going to deploy a GPU-driven machine learning model in these games. Second, what I'm going to do, and I said I was going to do, is we're going to do some very simple computer vision and some really complicated feature engineering, and that's going to be the approach. So for example, what you saw here was I wanted to analyze players' reaction times. And so what I did is I changed the shaders for the game to make everything black except every enemy, and then give every enemy a different color. So I could, do computer vision of count the blue pixels to compute when enemies were visible. And then, we're going to be able to evaluate all these different behavior components like reaction time in isolation of the general game. And of course, hey, if you want to do all this really complicated stuff, you better work in a game that you can actually modify. And finally, these special features that I was going to engineer were going to be so powerful that I was going to be able to just work on really small data sets of me and my friends playing the game. And these were sort of the 5 hypotheses I started the project with. And first one was wrong is, hey, modern machine learning can actually be really fast and really efficient if you're specializing to your use case. Yeah, GPT might require a GPU, but like, hey, if you're using a small transformer, you can get this running on one core of one CPU in real time. The second surprise is that game traces are really, really rich, and you can extract a lot of useful information. Yeah, you can extract things like position and key events, but you can also learn things like visibility and where people tend to interact from these game trace logs. And so if I was a game company today, I would be logging all of these game traces, particularly because anything derived from Quake 3, at least when they inherited the Quake 3 source, had these game trace log characteristics. They're called demo files. And so the next thing is you really don't want to evaluate these behavior models in isolation. So even when I was wrapping up this project, my advisors, Kayvon is a big fan of strong evaluations. And he said, hey, you got to reproduce the metrics from the self-driving car community, where they use this metric called min joint average displacement error and min joint final displacement error, which measure your ability over multiple trials to reproduce the exact lines that that were in the data set. And I personally didn't find these metrics too valuable because just running in a simulator, how well you can reproduce lines without measuring the impact of responding to combat and the complexity of the game didn't tell me that much about what my model was actually doing. The fourth thing is, and the one hypothesis I was actually right on, is if you're going to work on a game, you should really choose a game that you can modify and change. So here's a piece of source mod. It's a snippet of some code for modding Counter-Strike, where I was able to interface with the ray tracing component of the game so that I could compute visibility in real time, modulo the map geometry. And just having this ability to drop into the game and answer questions for yourselves is really crucial. And finally, I feel like I'm really at the starting point here. 123 hours is a bit of data for an academic, but these games can track so much data. I mean, I'm going to get the exact numbers wrong, but it's like Counter-Strike is like can have like 1 million hours of data every hour. And so if you were to stick to that fire hose and just drink from that data, you could have so much data to learn from to do things like improve fine-grained coordination, other rare behaviors, specialized models to individual player styles, or generalize multiple maps or games. It only takes an hour and a half to train the model. So and popular maps are played for years, so you could easily specialize a model for every different map. And so I'll skip the acknowledgments. Yeah, we don't need the acknowledgments. So I'd just like to thank my collaborators. They're really helpful. You can't do a PhD by yourself. You really need people to help you. So I'll ask any questions now, or I'll take any questions. I won't ask them.
Yeah, open-ended questions first, and I have a few questions for the class also.
Yeah, I was curious, so like you train the model on kind of like data of like players that kind of know what they're doing.
Yeah.
But like, for example, if I played against it and like I have no idea like really how to play this game. I mean, I know the basics, but I'm not gonna be very good. Like, does that throw the model out of distribution? Is that something you looked into or not?
So we wanted to focus on data that was publicly available, and these pro matches are publicly available. I would say I'll answer your question for the pro matches first, and then I'll bring it to amateurs. Even with pro matches, there's a lot of behavior in these logs that isn't particularly well organized. Things like how players mess around when one of their teammates is on a timeout in a bathroom break. So like my teammate's waiting for a drink of water, he's in the bathroom, and so I'm just going to mess around and do nonsensical things that you wouldn't want to learn from. And so one benefit of highlighting this subset of the game where
Question: is that a common behavior of the pros, though?
well, they're on stage and the logs are, the match started and we're calling a timeout because I got to go to the bathroom. Or like the match is split into 2 halves. And so the period in between halves, you're going to have a period where you're going to wait in between half times.
That's in the law.
Yes. And of course, Counter-Strike by itself doesn't have a defined many tournaments use their own implementations of these different things. And so you got to be very careful about filtering all this out. And so restricting yourself to a subset of the data where you know the human behavior makes sense can enable you to focus on things where you're going to get reasonable data. Now, pros might be more reasonable than humans. Humans may make things that are less sensical. And so one interesting long-term behavior would be think about a higher level model that coordinates long-term strategies. So one thing may be if you have a model, say like an LLM that's looking at these chat interactions and predicting long-term strategies, you can separate these different modes more easily. But there's a mix of being smart about your data and then thinking about higher level models in the long term.
Like, do you have any interest, or I guess what would you say the challenges for in integrating cognitive data of like players talking to each other?
I have not worked on that right now. I believe, don't quote me because I didn't work on those parts of the logs, that part of the data may be encrypted. I don't know. What-
Hypothetically, let's say
yeah.
you worked at Valve.
So that's how I worked at Valve. I would say that'd be very interesting. When we look at the way people describe the game, there's a very well developed, 2-decade-old history of language for describing the game. And I think learning essentially a model from language to state would be very powerful in learning long-term strategy coordination, and would be a very good way to have a natural language interface to the humans. Because if you learn something like, hey, if humans say 2 cat 3 long smoke Xbox, which for those who aren't playing is a set of words that make sense to a Counter-Strike player, and you could type those in, you could learn some type of long-term strategy model. Now that's a separate project that I have not worked on, but I believe that that's a very promising next step.
Yeah, correct me if I'm wrong, but I believe your evaluation, your benchmark was based on a professional
Yeah.
basis. If your goal is to kind of simulate like a human player, do you ever consider playing like testing against an amateur human with track?
So our goal is to replicate the human distribution, and our human distribution we have is pros. So it didn't seem right to measure against another distribution. Also, we needed to focus on a data set that we had, and I had a data set of pros. I don't, it would be different to go collect a large amateur data set. They exist. PureScale, I believe is the name. They're in the slides, has a large amateur data set. But again, they were focused on high level analytics, and there are a lot of weeds. So
How would you extend the project if your assumption of limited compute budget changed by a couple of orders of magnitude, for
Yeah.
example?
So the one thing I'd really like to explore, which is sort of maybe a curve, is games that have more units in them. So things like RTS or even or battle royales. So one thing about attention is that it scales quadratically with the number of tokens. And I'd really like to explore, hey, if there's 100 players on the map in PUBG, or there's 1 player and it's StarCraft, and there are 10,000 units, and you'd like to have some intelligent model that learns how all the different moves should move intelligently, I believe this would, change the performance characteristics. And so looking at something like a StarCraft model would be quite interesting.
And for Counter-Strike,
Yeah.
like, do you think it would benefit from being able to use a GPU, and how do you think you could?
Yeah. I think the challenge I ran into is the inertia problem. I think the real thing I'd want more of with compute, be more compute during training. So we're sort of, when you take a behavior cloning approach, which is the style of imitation learning, you get the very, very, very fast training performance. But you have things like the inertia problem and things like where, hey, the model hasn't seemed to learn from its own mistakes. And so a lot of the improvements in imitation learning or the hybrid imitation learning reinforcement learning work is about like, hey, learn a behavior clone bot and then have it play by itself or with humans, learn from its mistakes. And so if I had a much bigger training budget, you might explore things like, there's a very interesting algorithm from diplomacy called Pickle, PIKL, which is a hybrid imitation, which is like reinforcement learning regularized, but with an imitation learning policy. And so if you had a lot more compute, particularly in training, you could explore these policies, which are like, hey, make sure they look human-like, but still guide them towards winning. And that's probably what I would like to look at next.
Yeah, so you mentioned, I think you were talking about how you can't really find like really high level human-like strategies from just reinforcement learning, and that's basically imitation learning approach, is that correct?
I would say when you take a reinforcement learning approach, you would be concerned that it wouldn't cover the entire distribution. It might cover one strategy, it might cover a few of them.
David, there's also one.
Yeah.
The real reason that you didn't
Oh,
take
yeah.
a reinforcement learning approach is.
Oh yeah, the real reason is a compute budget. Is that like in order to do an RL approach, I would need to spin up, pardon, I would need to spin up lots of different games and have them all running simultaneously, and that compute budget was not within my.
So I was gonna ask about like OpenAI's tag one. that
Yeah.
they're building, and it seems like they discovered strategies that you couldn't discover.
Yeah, so I would say yeah. So two things is yeah. So they had the Quake 3 game, which they turned into a tag capture the flag game, and they did learn some human strategies. One challenge is that when they just let the bot run, it also learned an amazing aim ability, and so they had to work really hard on tamping that aiming, or not. They had to work on tamping that aiming ability down so that it didn't, so that the win rate went down from like 95% to something more reasonable. But even then, my concern would be 200 millisecond reaction time is not 200 millisecond reaction time. Meaning that if you always react at 200 milliseconds perfectly, it's very different from the variance of the human styles of reaction times. And so you need to be careful not just of like matching the exact outcomes, but matching the style of those outcomes.
Curious, did you implement like economy management and like coordination in the bot?
We were just focused. So those seem like problems like we saw with other techniques. And so I just wanted to focus on learning movement. And so I said that's out of scope. Everyone just gets one weapon, and everyone gets the armor of whatever the people in that situation had. And we're not going to model different weapon types, and we're not going to model economy management.
Which weapon did you use?
The AK, which had some interesting characteristics because some of the initial conditions were for pistol rounds, and so, but it just was a way to make sure we could focus on movement in isolation. Sorry.
How did you represent dead actors?
Great question. Those are the only things we masked out. So we provide all the tokens into the model, and we just and I just mask out everyone who's dead, and then you just don't use them when you're in the loss when you're training. So your loss outputs 10 tokens, and then you only apply loss for the subset of the tokens that are actually alive. And I did find that training without that mask did decrease performance. Or sorry, training, what was it? I believe training while seeing dead tokens did decrease performance as well. Yeah. But I didn't, I did one or two experiments. I didn't, push that to the end of the world.
I guess one question would be like, if there were a like black box API that came out tomorrow that could like perfectly produce, like it was super fast and you didn't know how it worked, but it could perfectly produce human-like movement of game bots. What would be like, for this project, like what would be kind of like the knowledge takeaway, or like what would we still gain from going through the process of implementing human-like movement bots? Like what do we learn?
So if all the tech worked magically, I would say the thing to take away would be the evaluation methodology. I would say the contribution of how to quantify humanness and how to look at these ways that we talk about the behavior in the world and to quantify things like teamwork would be something that we were taking away from.
I think another thing that
Yeah.
you taught me, or the project taught me, is I think it's pretty interesting to think about this of you want to do what humans do, you don't necessarily need to do it the way they do it. That was pretty interesting to me, is that like I definitely would have come at this as we've got to make them only see what a normal human would see. We've got to make them have dexterous capability that was very close to what they would do. And I just think it's an interesting example of the power of big data, which says, hey, don't worry about why or how, but just make sure it matches to some distributional characteristics. And that does place the emphasis on the evaluation, because now you really gotta know that it matches and stuff like that. But it's a great example of the sort of the big data camp going, doesn't really matter how it works, or even if you know what the model is attending to or thinking about. as long as it does what we want it to do, or what a, a reasonable human would do. In other words, it's human aligned,
Yeah.
to use their terminology. It can be kind of compelling.
Yeah.
And human, like doing something that does the same thing. I think this is an example of it being far easier to create, easier in terms of the sophistication of the modeling, the amount of data that's necessary, the runtime, than trying to make something that makes decisions a little bit more human, or like a human. And we talked in the class a lot about how that gets us into trouble in a lot of places. We can't control these models. If they do one thing, but we only want them to do something else, that really limits their applicability. I don't think we've gotten to that part of this project.
Well, we have gotten there. That was one of the big problems. The
Well,
same.
yeah, we have gotten there.
We haven't
We've
solved-
We've hit the same problem.
So I would say one of the challenges, particularly when you're trying to control these things with a behavior cloning approach. So the way you can control these things is that you can write control signals as inputs. This is very similar to the way you provide a reward function in offline RL.
Or just conditioning.
Yeah,
Just
conditioning.
Runtime conditioning.
But the problem with runtime conditioning, I find, is that if the conditioning signal is weaker than the rest of the features at predicting the next time step, then the model just straight ignores it. But if the signal is stronger than predicting all the other features, then the model sort of forgets some of the humanness. So for example, like when I was trying to force the guys to be more aggressive, I took two different approaches for that. One was like classify rounds as aggressive or passive and then feed that as a signal. And this classifier was like weakly okay, so it improved a little bit. It improved somewhat. I would say it improved somewhat, we'll say. Then I had another one where I said, hey, you're being aggressive if you're getting closer to the objective over the next 5 seconds. And this thing, stomped out all the passiveness. But the problem is it resulted in the model not having as much teamwork. Because the guys, were now running towards the objective more and not waiting for their teammates as much, because teammate positioning was a less important feature. And so the challenge, the game I had to play, at least in my stage, was balancing control with preserving the features of the data.
Okay, so maybe we'll do one last question and let everybody get out on time.
Oh, yeah.
And I'm sorry, and David, I'm sure could stick around and talk.
Yeah.
I was just curious, going back to like the compute constraints, but
Yeah.
like the compute constraints, do you try any strategies like maybe using auxiliary objectives, like predicting, masking out parts of the agent state and like predicting that state, or maybe like trying some kind of sample prioritization or replay strategies to see if you can kind of get more out of the data that you do have, or kind of reduce the computational burden of training?
No, I mean, so computers of training them or of deploying them, pardon?
Training.
I would say the training budget for an hour and a half was fine. We didn't the real constraint for these games is the inference budget. Now it's sort of a very nice result that you can train in an hour and a half, and I'm sure you could do better. I'm not, but the key thing here is it has to run in real time. If it took 3 hours or if it took 30 minutes, it wouldn't be the end of the
Well, I
world.
think this is
Yeah.
more of a data sparse
Oh.
than a training budget. So let me jump in.
Sure.
I think that, if you take the attitude that half the class argued when we had our data versus modeling discussion last week, you could argue that for David, like scraping the internet is a pretty inefficient way to get data, for a grad student. And so I think if you wanted to do more with your data, you would have to be more clever,
Sure.
right?
Yeah.
If David was instead at like a company where you could just like turn on logs and get 100,000 hours overnight, I think the first thing you would try in this case is don't be clever, just use more data.
Yeah.
Right, to get more complicated behaviors and more sophisticated stuff. Like, I think you would want to show that approach fails before you try to solve this with more sophisticated machine learning mechanisms and stuff like that.
Yeah.
Cool. Okay, so David's around. I'm sure if you want to keep asking questions, you're more than welcome to. We probably need to make sure the room is ready for the next class. I guess maybe if